so let's get started on Chapter 9. Chapter 9 is going to be introducing two new functional groups, aldehydes and ketones. We've actually already seen these before, so let's just remind ourselves. We got an aldehyde, and this one is a ketone. Both aldehydes and ketones, it really drives me nuts that these are considered two different functional groups because they have the same reactivity. They both contain, importantly, they both contain this type of bond right here. Does anybody remember what we call that carbon-oxygen double bond? I've brought it up like 3 or 4 times now, so that's a pretty good indication that it's going to be something that I feel like is fair game for an exam. This is a carbonyl. Carbonyl, that's that bond. That carbon-oxygen double bond is called a carbonyl bond. And so both aldehydes and ketones have that carbonyl bond.
I don't see a dad in your contacts.
Oh, I was like, who the hell? The big difference is what's attached to that carbonyl carbon, right? So the only difference between an aldehyde and a ketone is in an aldehyde you have a hydrogen attached to that carbonyl carbon, and in a ketone you have carbons on either side. Okay, all right, so this, I guess if I'm going to explicitly draw it in there, this is a methyl group, this is a methyl. Right, so that is the difference between an aldehyde and ketone, is what is bound to that carbonyl carbon, right? So then the simplest ketone would necessarily contain at least 3 carbons, because you have to have 1 carbon on either side of that carbonyl carbon. Aldehydes, that functional group is always going to be on the very end of the molecule, right? So this is a very small, simple aldehyde. If I were to draw like a big, ugly one, that carbonyl group is always going to be located on one of those terminal carbons, right? So it's kind of like a carbonyl group that's at the end of a molecule. Okay, so we've seen these before when we talked about, what did we call these? Dang it. All right, well, there it was. These would be oxidation reactions, where we convert alcohols to aldehydes or ketones. So these would have been what we called oxidation reactions. So if I start out with a primary alcohol, I'll get an aldehyde. If I started out with a secondary alcohol and I oxidized it, I would get a ketone. Okay. Remember we said, if you kind of remember back to general chemistry, you had this big complicated way of calculating oxidation numbers. I told you for organic chemistry we can kind of simplify things. When I say oxidation, I mean making more carbon-oxygen bonds. Right, so I'm oxidizing that primary alcohol or secondary alcohol to an aldehyde or ketone. I'm adding a new carbon-oxygen bond. Okay, so this was the first time that we had introduced these two functional groups. The homework that was originally for Chapter 8, I sort of pushed back a little bit because there's one new reaction that we have to know about here that's introduced in this particular chapter. And this is going the other direction. And these are what we call reduction reactions. All right, so reduction is the opposite of oxidation. So if oxidation is forming more carbon-oxygen bonds, reduction means that we have less carbon-oxygen bonds. What's up?
So the aldehyde, that only has like 1 hydrogen on that carbon?
It could have 2. The very smallest aldehyde that exists would be this thing here.
Okay.
Okay? This is actually formaldehyde, what's famous for preserving dead bodies. An aldehyde just has to have a hydrogen attached to the carbonyl carbon. Okay, so this is the very smallest aldehyde that you could possibly have, where there are two hydrogens attached to the carbonyl carbon. All right, anyways. So, going the opposite direction is what we call reduction reactions. So if we reduce a ketone, we get a secondary alcohol. If we reduce an aldehyde, then we get a primary alcohol. All right? So these are like the names of the reactions. Let's look at our actual reagents that we used. To get from a primary alcohol to an aldehyde. So this is kind of annoying because our textbook uses PCC is our weak oxidizer, but then our homework system uses DMP. So either one of these can be used to reduce a primary alcohol to an aldehyde. All right. If we have a secondary alcohol, we actually could use PCC or DMP, but they're way more expensive, so we wouldn't bother. We would use one of those chromium-containing compounds. So sodium dichromate. Actually, let me take this to a different page. All right, so let's just remind ourselves, do a little bit of review here. So again, for my secondary alcohol, I could actually use any of those reagents on the board. For the primary, I have to use the PCC or the DMP. Because what happens if I take my primary alcohol, everybody take a second and see if you can't remember what would happen if I did this here. Took my primary alcohol and hit it with that chromium-containing compound. See if you can't predict the product there. That's one that we should know from the last chapter. That's a question mark, believe it or not. Does anybody remember? It's called a carboxylic acid, but absolutely. So you get this fully oxidized carbonyl carbon, which now has 3 carbon-oxygen bonds. All right, so this is what we had called a strong oxidizer. And PCC or DMP is what we had called a weak oxidizer. So we want to make sure we have those 2 reactions of primary alcohols down. All right, but again, the new one that we're introducing here today is the reduction reaction. So let's take a look at the reagent we use for reducing. Good news is it's the same for all of them. We don't have this same strong weak consideration that we have to worry about or anything like that. All right, this reagent here is what we call lithium aluminum hydride, LiAlH4. Lithium, aluminum, hydride. All right, so that's our reducing agent. It'll both reduce an aldehyde to a primary alcohol. We can also use it to reduce a ketone to a secondary alcohol. We can actually use it to reduce a carboxylic acid as well. So it is just the go-to reducing agent here, sort of the reverse direction of all 3 of these oxidation reactions that I had put up on the board. Okay, so let's Getting a little busy here. Let me just color code. So these are these reduction reactions. All right, and again, opposite of our oxidation reactions, right? Going the other direction, creating less carbon-oxygen bonds. All right, so that would have been one that you actually needed for your Chapter 8 homework as well, is these reducing agents. All right, so now that we're sort of formally introducing these functional groups, every time we learn a new functional group, what do we got to do? Everybody's favorite. Nomenclature. And unfortunately, they are named differently. Aldehydes versus ketones. Aldehydes are going to have the suffix al, al, right? Not to be confused with alcohols, which were all, ol. So aldehydes are al, and ketones are ones. So let's just look at a few. Let's actually do our ketone first here.
So aldehydes are on the terminal carbons and ketones are in the middle?
Yep, basically, exactly. Both carbonyl groups, but one of them's on the end, one of them's in the middle, exactly. Okay, so the name of the game is the same. I mean, the good news about nomenclature is once you get that basic set of rules down, now we're just adding new suffixes to the game, right? Just new endings. Besides that, everything's the same. So the first step, as always, and I guess let's just explicitly remind ourselves of how we do the nomenclature, is we got to find that parent chain, that longest continuous set of carbons. That's always our first step, is to find the parent chain in the molecule. Okay? Now we have to, well, really the second step, although it doesn't apply in this case because there aren't any, is we would name our substituents. Whatever's hanging off the parent chain. So in our ketone here, I'm going to find my parent chain, my longest continuous set of carbons. That would be 1, 2, 3, 4, 5, 6. Okay? I kind of think about nomenclature, I kind of build it from the back end, right? So the first thing I do is find and name the parent chain, right? Then I'll start decorating it with the substituents. But when I'm doing nomenclature, really the first thing I would put down is that I have 6 carbons. What prefix is 6? Hex. So this would be a hex unknown. All right, now I have that own ending for my ketone. All right, and then, so if I had substituents, I would name those as well. Those would be like if I had a methyl group or an ethyl group or something sticking off. I don't have that in this particular molecule. We'll do some more complicated examples that do. But the last step here is to number, well, I guess the next step here is to number that parent chain. All right, so there are always 2 directions that you can number. The one direction, or the reverse direction. Okay, so looking at my 2 numbering schemes here, which one do we think is correct? Who thinks it should be the red numbering scheme? Who thinks it should be the blue numbering scheme? Why the blue? Because it puts that ketone on the smaller number carbon, right? So this is indeed, I'm going to pick my blue numbering scheme. I'm just going to get rid of this so we don't get confused. So this would be 3 hexanone. Everybody take a second and draw me 2-hexanone. Alright, so now I'm going to draw my 6-carbon parent chain. I'm going to put my ketone functional group, that carbonyl bond, on the 2nd carbon. That would be 2-hexanone. If you put it, on the second from the last one, that would be equivalent, right? If I take this molecule and flip it over like a pancake, it's the same molecule. Cool. The last step would be to put it all together. And so that's what I did by putting that number out front, 3-hexanone, 2-hexanone. So this is kind of the same 4-step procedure that we use for naming any compound here. So now we have our aldehyde. Again, the suffix for the aldehydes are al. So this would be hexanal. Okay? The weird thing about aldehydes, so you can put a little star, we do not have to number our carbonyl bond in an aldehyde because it's always on the end. So it would just always be carbon 1. So rather than saying 1-hexanal, 1-pentanal, 1 whatever anal, because it's always going to be on carbon 1, we just don't put the number. Okay? Importantly though, this carbon here, if we were to have another substituent, this carbon here is always carbon 1. Okay? So again, that's why we don't bother numbering it, is because we already know that that carbonyl carbon is carbon 1, but that's going to be important for if there's another substituent in the molecule. We need to make sure that we put that carbon as carbon 1. All right? So let's do some more complicated examples. We'll leave our instructions up here. Let's do an aldehyde. Ketone. So everybody take a second, see if you can. If you can name the whole thing, fantastic. At the very least, I want you to be able to find that parent name, find that parent chain. That's the first important bit. All right, so got to find that parent chain. So in my aldehyde, we'll do this first example. My parent chain would be these 1, 2, 3, 4, 5 carbons. All right, that's my parent chain. I'm going to go ahead and spy everything else in my molecule here. Remember, the whole point of naming in organic chemistry is that we can uniquely point to a specific molecule. So I have to make sure that all of my carbons are accounted for. This thing right here, what we call that? as a substituent. Yep, that would be a methyl group. So check, check, got my substituent. Now I need to number my parent chain. And this is the bit with aldehydes that we need to make sure that we're really good about. Always putting that carbonyl carbon as carbon 1, right? I'm not gonna bother numbering both ways like I will with my ketone because I know already that this right here is carbon 1. Let me actually use a different color. All right, so then I have to number my parent chain. And then I'm gonna put it all together. So this would be 3-methyl. And I knew my parent chain was a, what's 5? Pent. Pentanal. All right, and my ketone, how many carbons are in my parent chain? Also 5. I'm not very creative, apparently. 2, 3, 4, 5. Now I gotta name my substituent. In this case, it's this fluorine here. What do we call that as a substituent?
Fluoro.
So that's a fluoro group. Okay. Now I'm gonna number my parent chain. One, 2, 3, 4, 5. Okay. Okay, we're going to make a note under number parent chain. We saw this with regard to alcohols as well. Same thing is true for aldehydes. Well, really, ketones is where it matters because aldehydes, we already know what carbon 1 is. We're going to prioritize the carbonyl bond. All right, that means I'm going to make sure that that carbonyl group has the lowest possible number in the name. All right, this is actually not a great example of illustrating this. So let me just do another one real quick. Very similar. 5 carbons in my parent chain. I would go to number my parent chain. I'm going to do it both directions. 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Again, what it means to prioritize that carbonyl group is to make sure that it has the lowest possible number. Right? So in my red numbering scheme, the carbonyl would be at 2 and the fluoro would be at 4. In the blue numbering scheme, it would be exactly reversed. The fluoro would be at 2 and the carbonyl at 4. But again, I'm going to prioritize that carbonyl group, so I'm not going to use my blue numbering scheme. I'm going to use my red numbering scheme. All right, so this would be 4 fluoro, 2 pentanone. All right, again, because I'm going to make sure to prioritize that carbon-oxygen double bond, that carbonyl bond. The reason I said that that first one that I drew was a bad example is because they're both carbon 3, right? Both numbering schemes put that carbonyl group on carbon 3. So in this case, when they're tied, then I'll look to the other one and make sure that it has the lowest number. So this would be 2 fluoro, 3 pentanone. All right, here I'm actually going to pick that bottom numbering scheme. All right. All right. Let's just do a bunch more. Let's just make sure we got this down. you're going to number based on like where that other functional group is. When you put it together, when you assemble, it goes in alphabetical order. That's a good question. All right, so I'm actually going to start at the end here. I kind of did them hardest to easiest for no good reason. Procedure is the same. We're going to find our parent chain. So 1, 2, 3. I have that ketone, right? It's in the middle of my molecule, so it would have the -one ending. And this, it would be on carbon 2. It would be the same either direction, so I'm not going to bother with both. So 2, prop, unknown. Okay. Now, this what we like call the systematic systematic nomenclature, where we have this set of rules that we follow in order to get these names, right? This is what we call the IUPAC name, because that is the organization that established those rules in like the 70s. A bunch of scientists got together and decided, all right, we need to call everything the same, because y'all are calling it one thing, I'm calling it another thing, nobody knows what anybody's talking about, all right? So that was this IUPAC, the International Union of Physical, and I don't even know what the heck. Anyways, group of scientists got together, decided this is how we should name stuff, right? But truthfully, stuff that was like super in common use, they have what's called a common name that just like stuck. Nobody ever refers to this molecule as 2-propanone. This is acetone. All right, that's the common name for that particular molecule, and that is literally the only thing you will ever hear referred to. I hate teaching systematic names and then being like, oh, by the way, there are all these common names you have to memorize. So I like oftentimes gloss over it. For this particular one, we got to know it, all right? Acetone is just the most universally used organic molecule in and outside. If you ever use nail polish remover, it is most likely acetone-based. So this right here, we are actually going to have to know the common name for. This is acetone, our simplest 3-carbon ketone here. Okay. It's the only one, I promise. All right. 3-carbon, so again, for this one, same procedure. We are going to find our parent chain. There are 3 carbons in that parent chain. I'm going to go ahead and name my substituent as well. Chlorine we would call a chloro group. And then I'm going to number my parent chain. Again, because this is an aldehyde, I'm going to make sure that that carbonyl carbon is carbon 1. All right, so 1, 2, 3. Then finally, assembling it, put it all together. This would be 3 chloro propanal. Cool. All right. To this next ketone here, I gotta find my parent chain. How many carbons are in my parent chain? 6. All right, so 1, 2, 3, 4, 5, 6. I'm gonna name my substituents. These guys here, what do we call bromines? Bromo. So these are bromo groups, and I got 2 of them, right? So I'm gonna have dibromo in my name. If I number my parent chain, I'll go one direction. I'll go the other direction. 1, 2, 3, 4, 5, 6. All right, so let's vote. Who thinks it's the red numbering scheme? And who thinks it's the blue numbering scheme? Awesome, because we're going to prioritize that carbonyl group, meaning we're going to make sure it has the lowest numbers. So it's indeed the blue numbering scheme that's correct. So when I put it all together, my last step is to assemble the name. Remember, you're going to have to put the location of both of those bromines, even though they're on the same carbon. This is definitely like the most common mistake that I anticipate people making would just be to say 4-dibromo. Right, you got to put the location of both bromines, so this would be 4,4-dibromo. Every functional group has its own, or every substituent has its own number associated with it, regardless if they're on the same carbon, right? So 4,4-dibromo 2-hexanone. Right, because this was 4,4-dibromo, but it could have been 4,3-dibromo, right? So even though they're on the same carbon, we need to put both of those numbers. All right, and then my last one here, how many carbons are in my parent chain? 7. What's my prefix for 7? Hept. Yep, so 1, 2, 3, 4, 5, 6, 7 carbons in my parent chain. I'm going to name my substituents. A 1-carbon substituent is a methyl group. And what about this one? This one's 2 carbons. So this would be an ethyl group. Awesome. I'm going to number my parent chain, and again for aldehydes it's a little unique. We don't have to do both. We automatically know that this is going to be carbon 1. Okay. So that means that I have an ethyl group on carbon 3 and a methyl group on carbon 6. We created this short little cheat sheet here, and step 4 was to assemble the name. All right, we're going to add another little note to our assemble name step, which are substituents. Go in alphabetical order.
I keep forgetting if there's like a dimethyl or a diethyl, like just how does that do oxidize either?
Oh, you ignore the di.
Okay.
Yeah, so you would just base it off of methyl or ethyl.
Okay.
Kind of a pain in the butt.
I keep forgetting.
Yeah, it's a very easy to mix up. So again, so now I'm going to assemble my name. I'm going to make sure to put these substituents in alphabetical order. So 3-ethyl, 6-methyl. Heptanal. Remember, I don't have to bother saying 1-heptanal because it's always at carbon 1. All right, so this is our nomenclature for aldehydes and ketones. There's 2 kind of special cases I want to point out real quick because I know that they're going to be, I've seen a few examples on the homework. These are things that honestly I'm just going to tell you because I've seen them on the homework, but we're not going to get too bogged down. If we have something like this, where we have an aldehyde right next to a ring, this has its own stupid name associated with it. First of all, that ring we would call what? Cyclopentane, right? So that ring, this would be cyclopentane, and then that aldehyde portion is carbonaldehyde. Super stupid.
No, will this be on the exam?
It will not be on the exam. It will be on your homework. So that's why I just want you to make sure you have this example in your notes that you can refer back to if it throws that up at you. Okay, that's like when you have a ring, an aldehyde group sticking off of a ring. That's how it's referred to. Okay. The other one is that I want you to have in your notes, just in case they throw you one of these, is if you have two aldehyde functional groups in the same molecule. Notice that they have to be located at endpoints, right? Like, there's no way to do it where one of them is going to be in the middle and one of them is going to be on the end for them to both be aldehydes. So if they're aldehydes, they have to be on a terminal carbon. So actually, the name of the game is the same in terms of finding your parent chain. 1, 2, 3, 4, 5. And because I know they're on terminal ends, I know one of them's on carbon 1 and the other one's going to be on the last one. So again, you actually don't have to put the number in here. So this would be pent. And then how do we think we refer to two aldehyde groups? Dial. So it's going to be dial. Okay. Like so, di-al. The weird thing is that whenever in organic chemistry you're about to smash two consonants together, they always stick an E in there. So it's not pentanediol, it's pentane dial. There's an E in there. Okay, going from name to the structure, I don't think is too bad, but if they did ask you to name it, you'd want to make sure to have that E in there. And again, this is just kind of a common thing in organic chemistry. Whenever we're about to stick two consonants together, they stick an E in there. Okay, so it's not pentanediol, it's pentane dial. So anyways, I want to make sure you guys have these two example in your notes in case they throw them at you. Knowing how to name the rings is not something I'm going to get too hung up on. Okay. Cool. All right, so we actually talked about these. So we've talked about the oxidation back in the alcohols chapter. The last chapter we were talking about ethers, and we spent a lot of time talking about ethers as solvents. Well, it turns out that the reaction that we learned there, the functional group that it uses, is an aldehyde or ketone, right? So these are reactions that we were first introduced to last time that we want to make sure we have down. Anybody remember the very weird name? Grignard. These are Grignard reactions. And remember, these are, first of all, they're really important in organic chemistry. They're one of the basic reactions that you would do in the lab to create new carbon-carbon bonds. They're cheap, it works well, it's just like kind of the perfect storm of good organic chemistry reactions. So definitely something we want to make sure we have down. Everybody take a second and see if you can't get me the product of these here. So I'm going to put my product down and then I'll walk through sort of how I did it. So just so you guys can check. Should have a 6-carbon alcohol where that OH group is on carbon 3. All right. And so I sort of said it walking through this procedure. I've done it a bunch in terms of like illustrating with colors and all that good stuff. I'm actually going to explicitly put down kind of step by step so that if you guys get stuck, you have some sort of a strategy guide that you can look to in your notes. All right, so how I would go about doing this. So again, this is my target here, but now I'm going to do it step by step. I'm going to draw my aldehyde or ketone carbons. Aldehyde. Sure. Sometimes words just don't look correct. Aldehyde or ketone carbons. Right? So again, I'm not losing any carbons in these reactions. It's very important to make sure that you have the same number of carbons on one side as you do on the other. So the first thing I'm going to start with is my aldehyde or ketone carbons. I'm going to put down those 1, 2, 3 carbons. Okay? Now there's going to be an OH group on what was formerly my carbonyl carbon. So this carbon here that used to be a carbonyl carbon over on the reactant side, that's the one that gets that alcohol group. Okay? And now there's going to be a new carbon-carbon bond between my carbonyl carbon. So again, that was this one that I highlighted in orange here. And the carbon attached to the magnesium. Okay, so my new bond is going to be between my carbonyl carbon and this carbon here that was attached to my magnesium in my Grignard reagent. All right, so you need to make sure you link these together at the right place. Right? So then last thing I'm going to do, once I know how I'm going to link them, I'm going to then draw the carbons from my Grignard. All right, so now I know that this should be linked to that green carbon there. I'm going to draw the back half of that molecule. All right, that's how I got my product. All right, this was my aldehyde. This thing with the magnesium, again, that's what we call our Grignard reagent. Okay, and actually, it's kind of bizarre to me, and I studied chemistry a whole long time. These things are very easy to prepare if you start out with an alkyl halide, an alkyl bromide, and you just add magnesium to it. It's kind of amazing, but the magnesium will insert itself between the carbon and the bromine. Okay, so actually your OWL homework will ask you for the aldehyde or ketone and the alkyl halide that you use to prepare the Grignard. Okay, so if you know what your Grignard is, basically you just take that magnesium off, and that is your alkyl halide. All right, but again, you start with that alkyl halide and you just toss in some solid magnesium metal. Pretty amazing. All right, so let's do another one. We'll make it a little bigger and uglier to make sure we have our procedure down. Take a second and draw me the products of this reaction, the product of this reaction here. Sometimes they're good, sometimes they're bad. I don't know. I've been doing it forever. Like I said, if there's one skill you walk away from this class, it will be drawing hexagons. I have that down.
Yeah, I draw houses too.
All right, so again, I'm going to start with my aldehyde or ketone carbons, my 3, right? And actually, everybody take 1 second and count your carbons. Make sure you have the same on both sides of your chemical equation here. Easiest way to make sure you didn't make a mistake. Cool, so I'm going to start off with my 3 carbons that were my aldehyde or ketone. And now I'm going to put an OH group on what was my carbonyl carbon. So this middle one here is now going to have that OH group. Now I'm going to leave it a little bit of room because it also has to have that new carbon-carbon bond with the carbon that's at the base of my magnesium. All right, so now I'm going to put that in there. That's this green carbon. And now I just have to draw the back half of that molecule. That's not right. 1, 2. Oh, no, it is.
Yeah.
Why does that look wrong? Okay, no, that's right. Should have sounded a little bit more confident there. Yes, all right, correct. Here we go. Yes, anyways, and I can double check. I can convince myself. It looked a little weird to me, but nonetheless, 1, 2, 3, 4. 1, 2, 3, 4. And if you want to go further, okay, I got 1, 2. There's where that branch point is. 1, 2. All right, I'm good. All right, so there is my Grignard product that I would get. All right, remember the other thing that we want to be able to do here for these particular reactions, this was the first set of reactions that not only did we want to be able to predict products, we also wanted to be able to work backwards. So we'll do a few examples of this next time. We've done a few before, but I want to make sure we all got it down here. So for example, if I had this alcohol here, what would make my Grignard and what would be my aldehyde or ketone? Generally speaking, there's 2 different ways that you could do it. There's 2 different methods that you could do. Whether you say that this is your new carbon-carbon bond, that would be one set, or this is your new carbon-carbon bond, that would be another set. Either one of them would be acceptable. Okay, but we'll sort of pick up with this particular example next time.